Now it's the same sort of thing we did just a minute ago. I want to know what KSP for uranium-3 hydroxide is. So I gave you this thing. There's uranium-3, uranium-3, and that must be a concentration cell. Now what I do is I can tell you it's buffered at a certain pH. In this case, I gave you the hydrogen ion concentration. But as soon as I tell you what the hydrogen ion concentration in the cell is, what else have I told you? The hydroxide, sure. So all you have to do is solve for the missing uranium concentration. And I told you that the right electrode is a cathode, so that means this is the reduction, so that's the higher concentration. This must be the lower concentration. So that's the numerator, this will be the denominator when you're setting up that problem. Then you solve for the uranium concentration. Then you have the hydroxide ion that you get from this Q times the uranium you get here gives you KSP. And the other thing I always comment about this is that when you're working and you're measuring these KSPs, or these cell potentials, the electrode probably senses only the number of ions that are picometers or less away from the surface of the metal. You get a little further, it doesn't sense whatever ions are out there because it has to have ions bombarding the surface essentially to give you a cell potential. That's why you see some of these cell potentials where you get 10 to the minus 199 or something, because if you make a very small, if you have a 1.1 volt or 1.2 volt, you start getting these huge, or these really small numbers, small negative exponents because of that. So some of those numbers are imaginary, because if you just look at bismuth sulfide where it says KSP is 10 to the minus 99, if you calculate how many bismuth ions are in the Pacific Ocean or something, that used to be one of the problems in one of our textbooks. They gave you the volume of the Pacific Ocean. You'd find that there were like 3 or 4 bismuth ions in the Pacific Ocean. Okay, and that's pretty illogical, because one of the statistics in one of the old chemistry books, if you take a cubic meter of seawater, you can find almost every single element, the radioactive ones. So, and they say measurable. They never really said what measurable is, but nowadays 10 to the minus 9th molar is easily measurable in analytical chemistry. So measurable means that there must be more than, if you had only 3 bismuth ions, what would it be? 10 to the minus 23 or 10 to the minus 24 moles. 3 over, I would add those numbers. So that means there wouldn't be, that's way too small, that's all I'm trying to say. So you get these unrealistic numbers because they do come from measurements like this, where you're measuring cell potentials, where you have some of the insoluble substances present. And there's the problem we just got done doing, cell potential. Oh, I guess that's the one I did. What is the pH cell? Then this is starting organic chemistry, which is one of the next topics. But before I do that, we have to talk a little bit about electrochemistry. We talked so far, all we've been talking about are the galvanic cells. We're calculating cell potential, we're measuring cell potential. It's always dealing with the spontaneous reaction. These are going to produce batteries. This slide. Hope you don't get busy reading sideways. Straighten that projector up. So yeah, we talk about different types of cells. We talk about the primary cell. You still see them around. You can still buy them. Even the alkaline batteries are essentially primary cells because you can't recharge them. And secondary cells, you recharge them. NiCads, your car battery, all of those things get rechargeable. These are special new modern things that they put together. We'll mention briefly. But notice there's not too much in the way of problems in these things, but it's descriptive, and you should know a little bit about it. And that's the terminology that goes with it, either chargeable or rechargeable. And they always talk about this in every chemistry textbook. You probably can't go out and buy one of those anymore. You may not have ever seen one of those. Those were the old-fashioned old batteries. You put them in your flashlight, and 3 months later the thing had rotted out and your flashlight was a corroded mess. You couldn't use it. So I don't think they sell those. I haven't seen them in stores in a long time. I don't shop in stores. But they always talk about it because, I don't know, this was the common battery when all of us went to school, not you. All the people at my age that write textbooks. Okay? So they always toss it in there. It's got manganese dioxide and carbon, a black paste, got a graphite rod, producing 1.5 volts, just like most of our other batteries are set up that way also. It depends on the difference in the cell potentials. You have the zinc metal can. Because of the way this is set up, you slowly corrode away the metal can, and then all this inside material flows out into your transistor radio, whatever you had in those days. But they always talk about the reaction. Zinc is easy. And this one, when I went to school, they gave us 2 or 3 different reactions and said pick your choice. Most textbooks now pick that as the standard reduction half reaction. And you can look those 2 things up in the table. You have to put the acid base in there, you get an overall charge balance. And this is the thing that's the problem, because that's a solid, but it's a soluble solid. And so eventually the zinc case corrodes away. So what did they do? They put it into a more basic situation. These are our alkaline cells. But if you wait long enough, what's going to happen with those too? They corrode away too. It just takes several years instead of several months. So they do eventually corrode. And again, it's because of that basic material. But notice, let's go here. This is different than the diamine zinc. Actually, it should have been tetramine zinc, but he wrote diamine. But the zinc chloride that he wrote in the other was soluble, whereas this is insoluble, so it takes longer for the case to corrode away. So this is our alkaline cell, but it's a very similar reaction for the, in other words, this instead of having zinc hydroxide, you made it more basic, and you figure that would make it disappear faster, but because you're making the insoluble zinc hydroxide, it's that'll last a bit longer. And here's the one that you use all the time. This is your lead acid storage battery in your car. One of the plates is lead, the other is lead dioxide or lead fluoroxide, and he shows you charging and recharging. You have sulfuric acid inside your battery case. There's the reduction half reaction with the lead fluoroxide going to lead sulfate. And that's the sulfuric acid in there. He didn't put SO4 2- or whatever, he put HSO4- principal species. Here's the oxidation half reaction. Again, both of them produce lead sulfate. And here's the overall reaction. If you are starting your car, these things are reacting that way to make lead sulfate. Once your car is started, the alternator in the old days, we used to call it a generator, reverses that reaction. That's why it's a secondary battery. And there's the cell for potentially, you say, I never had a 2-volt battery. In fact, the old cars used to have 6 volts. That's because they hooked 3 of these cells in series. New ones are 12 volts, so they hooked 6 of them in series. But each cell is the same half cell that you see up there. You just have them in series so that the voltage multiplies. Somewhere they're talking about 24-volt batteries and things. Start your car even faster. I don't know. That's really an advantage. You don't see much about it, so maybe it's not that popular after all, or it didn't work out that way. So anyway, this is the battery that you have, and each one of those cells produces 2 volts. In the old days, there used to just be 3 in series, now there's 6 in series. what's the difference between a 2-month or 2-year battery and a 6-year battery? About $80, right? Or $95. I guess they're getting more expensive. I just had to buy a battery for one of my cars. But one time, a long time ago, when I first moved to California, I had a car. The battery went out after 3 years, like they usually do. And at that time, you could buy a lifetime battery. Okay? And the lifetime battery counted on the fact that it was still a 3-year battery, but most people in California didn't keep their cars more than 3 years. And so it wasn't the battery died, they figured the owner died, or they got a new one. But I kept my car for about 12 years, and I got 3 brand new batteries. You can't do that anymore because now it's a prorated warranty. But there are different batteries out there. Some of them are rated for 3 years, and sure enough, 3 years and 1 month they go bad. Others are rated for 5 or 6 years, and sure enough, after 5 or 6 years they go bad. How do they work that out, or how do they do it? Well, they all make lead sulfate as a product. And the lead sulfate accumulates on these grids as the battery discharges. So if you put a better grid material there, you're less likely to lose lead sulfate so it can recharge. Because if you get too much lead sulfate on the flakes, it flakes to the bottom of the case, and that puts a short across the inside of the battery. And now you can't fix it. They can pump the sludge out, I guess, and put some more sulfuric acid in, but it gets worse and worse. So basically, the difference between your longer life battery, they put this compartment a little bit bigger so they can get more of a sludge. What happened?
It fell even more.
That thing's going to come down. Don't sit there. Don't sit under there.
Oh my god.
Uh-oh. Let's stay away from this area. Everybody move into some other areas here, just in case.
That is gonna fall.
That's gonna fall right there. So just move. It's gonna come straight down though. So don't sit under these 3 seats. These 2 seats, wherever it is. I'll get to the quiz in a minute. So anyway, I just wanted to point out, they put better grid material on the more expensive batteries so the lead sulfate won't flake off as rapidly. And then the other thing is they put a deeper reservoir, and they can still do the statistics and predict exactly how long it will take. The way you can avoid that, if your battery is always fully charged, you have less lead sulfate building up on the grids. And so if you have a lower amount of lead sulfate on the grids because your battery is always fully charged, then you're less likely to have it flake off and shorting into the bottoms. The moral is, if your alternator comes on and you're not charging your battery, get it fixed before you have to buy a battery and an alternator. Okay, moving on to the other types of batteries. There's our famous NiCad battery. Now these are the ones that are rechargeable, and again they have lifetime so that you can recharge them forever, but it has to do with the preparation of the electrode. Notice you're making 2 solid materials, and the idea is that it expects it to go backwards and forwards easily, but as you make too much of the hydroxides, they're not going to be easily reversible. In other words, one of the reasons we don't let our precipitates dry out in the laboratory, in the next step where it says add some acid, it'll dissolve. Lots of times they don't dissolve until you boiled them and heated them and added acid for a long time. It's just that theoretically they should dissolve, but the fact that you get all these mixed hydroxide precipitates eventually makes it so it doesn't recharge fully. And they have what they call memories. In other words, the memory in the battery that says it shouldn't discharge any further is that you're making that mixture of hydroxides. Here's the new important thing. They're very expensive, but it's the fuel cell. And basically you're putting in water and you're getting out hydrogen. Putting in hydrogen oxygen, you're getting out water. And generating electricity in the process. So you're breaking down, you're combining hydrogen and oxygen to make water, and it's a redox reaction. So there's the oxygen, the hydroxide, and you add it together, you get hydrogen plus oxygen. So your 2 half reactions. And these are what? Essentially non-polluting, except you have to carry a source of hydrogen, you have to carry a source of oxygen in your car, and they tend to explode. Keeping an eye on my projection. Okay.
That's crazy.
So, one of the things they had about 4 years ago, they said at USC they developed something where you could carry methane around and break the methane down to hydrogen, oxygen, or actually got oxygen from the air. You break the methane down to hydrogen, a source of hydrogen. But yeah, don't let the doors stay. That might keep it up there for a little longer. Okay, so this is the fuel cell. This is modern technology. If you're going to the moon, what type of battery do you have? A fuel cell. Okay. You're driving around the streets, and I think BMW makes one fuel cell powered 730i, and if you have 150 to 300,000 over the regular price, you can get the fuel cell version. I don't know. I still think you have to carry tanks of hydrogen and oxygen. They get much higher voltage out of that. They talk about the cell efficiency. We don't do any calculation with that, but that's a very efficient cell. Most dry cell, most of these batteries that we use are fairly efficient in this 0.7 to 0.83. That's a really high range. We don't do it. There's the non-spontaneous reaction. Okay, galvanic cell, it goes one way. The other thing, how do you make it go the other way? Remember I talked about the potentiometer? You just put a higher voltage on with the terminals reversed. And that's the same thing that happens with your generators and ammeters, generators and alternators. They generate voltage at a higher potential than your lead cell produces, so it forces the reaction in the non-spontaneous direction. There's one problem we will do with that, but I'm not going to talk about it today. And it says predicting electrolysis reactions. There's so many things that go wrong, we're not going to worry about that. That was the thing where you get all the side reactions. Somebody asked about this with iodine. This is the one we want to come back to. I'll talk about that next time. Okay, I guess I didn't put down my rusting of the metal slides. But when something rusts, it's because you have reactions that aren't really the ones we're looking for, redox reactions. Okay, then let's do our quiz.